Welcome to Groundwater Talk Live. I am the groundwater guy, Tom Ballard, and happy to be your host today. Today, we are going to be talking about pH. So, I like to call it the one ring of water quality parameters because it factors into so many different discussions about different water quality parameters. It affects different measurements we make and what we can do in the well and things like well rehabilitation. So pH is a really important component, but some people just don't understand it. We think we understand on the basic level that it's acid and it's more basic or alkaline constituents, and that's kind of what we think about it. But how does pH really work, and how does it affect what we do and some of our other water quality parameters? So that's what we're going to talk about today. And so before we get going, it really helps me if you can like, comment, or share this video. It helps the algorithm, helps the word get out there so more people see it. We can get our subscriber base up and get more exposure, and that just helps me. So, even if you can just like it, I respond to all comments. So feel free to drop a comment, and I'm happy to chat with you. So with that, let's kind of dive in here a little bit and talk about pH and why it's so important. And this is just kind of a quick illustration here of, I thought it was kind of clever that I pulled this down of different test tubes with the different colors representing, going from on the right, the more alkaline to acidic on the left. So pretty clever representation. We'll talk a little bit about the pH scale, but before we really dive into what pH is, we just kind of need to understand how groundwater actually and water in general actually works. So water in and of itself will self-ionize, so it'll dissociate the H2O into roughly equal concentrations of hydrogen ions and hydroxyl ions. And so that's going to, when those are in equal concentrations, we're going to get a neutral pH. If this balance is upset, then the water will shift one way or the other depending on what the factors are that are gonna change that. It'll become more acid and alkaline. So things like dissolved gases or dissolved minerals in the water can unbalance the hydrogen and hydroxyl ion, producing alkaline or acidic pH in the groundwater. So hydrogen ion, basically you can see here we have the constituents of H2O. It'll dissociate into a hydrogen ion, which has a positive charge, and a hydroxyl ion of OH, which has a negative charge. So when these are in roughly equal proportions, you're going to get a neutral or pH right around 7. And we'll look at the scale here in a minute just for comparison purposes. So pH then, one definition is the pH is the concentration of the hydrogen ion, which when in excess of the hydroxyl ion is considered acidic. So the more of the hydrogen ion, the more acidic the water is. The more of the hydroxyl ion, the more alkaline the water is. So that's how the shift occurs. So another way to look at that is just pH is just an expression of the hydrogen ions in the solution. So that's all pH is. We're measuring that. There's a number of different ways to measure that. Everybody's familiar with the high school litmus paper, or that tell us if it was acid or basic. You can actually get color-coded pH to tell you more exactly what it is. Professionals tend to use a pH meter, an electronic meter in the field, but they all basically work the same way as detecting the level of hydrogen ions in the solution and determining how acid or how basic or alkaline the water is. So this is your pH scale kind of illustrated here. We can see on the top we're more acidic, going all the way to more alkaline on the bottom. And on the left there we have some for comparison purposes, you go from a pH of less than 1, battery acid. Gastric acid is the acid that's in our stomach to digest our food. So we have a pretty acidic stomach when you really think about it. vinegar 2.5. Pure water, distilled water at 25 degrees Celsius room temperature, then is going to be about a pH of 7. You're going to have equal hydrogen and hydroxyl ions in there. That's going to be considered neutral. Um, Seawater tends to be a little alkaline, so 7.5 to 8.4. And then we get into things like ammonia and getting up above 11. Bleach is going to be very alkaline. And then, of course, lye, 13 to 13.6, so very alkaline. It's used in a lot of harsh soaps and stuff like that because the alkalinity has those properties of that'll help clean things. So that's your general pH scale. Back getting into the definition, it's important to understand that pH is a logarithmic scale. So if you go from a pH of 7 to 6 becoming more acidic, that's actually a jump of 10. So 7 to 5 is 100. So it's a logarithmic scale. So it's not just arithmetic, it is logarithmic. So you can see you get down how much stronger the acids are down in the 1 or 2 range as opposed to getting right around neutral because it is a logarithmic scale. So 7 to 14 considered alkaline, 0 to 7 is considered acidic, and that's generally our scale there. All right. Implications of pH. So how do we start to use this in looking at our groundwater? So as the pH moves from 7 to 1, shifting to more acidic, then the water becomes more corrosive and minerals become more soluble. So this is part of the reason we use acid in well rehabilitation, because we're trying to remove the minerals in a lot of cases from the well, and more acidic solutions are going to take those minerals into solution. Also, if you have a steel casing, then the more acidic the water is in the well, then the more likely that is to corrode more quickly. So yes, definitely acidic water is more corrosive. As water becomes more alkaline, shifting from 7 towards 14, now what happens is minerals tend to precipitate out of solution. So this is where we have problems with the mineral scaling in the wells, is if our pH is relatively high and you are in a situation where you have, for instance, calcium carbonate dissolved in the water. Those are hard water, for instance. Those are going to be situations where you're going to start to see mineral scale developing. So we do want to pay attention to pH this way, because pH plus calcium that's near saturation will result in calcium carbonate precipitating out. This can work the same for metals like iron as well, although a lot of times with a lot of these things, it's not a straight chemical mineral precipitation. There's usually a biogenic component. We're not going to get into that today, although the bacteria in the well can affect the pH as well, and we'll talk about that here in a little bit. But generally, just looking at it from a simplistic standpoint, that as you become more alkaline, you see minerals saturated in the water, you're going to have a situation where you're going to see precipitation. So this is really why we want to monitor these parameters in a well to see, do we have active precipitation of minerals going on in the well? How fast is that occurring? And that helps us plan for well rehabilitation and to know what's causing our plugging. So other factors there as well, but we want to look at a host of parameters, and pH is going to be one of those. Calcium carbonate saturation is going to be another one, and other minerals, the mineral loads in the water is going to tell us if we have precipitation going on. So important component here. So some of the things that water quality parameters that we look at that are impacted by pH or related to pH anyway, and the first one of those is alkalinity. Now, I did a show on this a few weeks ago, alkalinity and hardness, but for purposes of our discussion today, is total alkalinity is a measure of the capacity for water to resist changes in pH to become more acidic. This obviously becomes important when we're looking at rehabbing a well because we're generally going to be using acids. And so alkalinity is going to impact the amount of acid we use and the concentrations of the acid. So related parameter to pH, because the pH is, or the shifts in pH that we want to make during well rehabilitation are going to be impacted by the alkalinity of the water. So alkalinity is determined through the titration process. So basically what you do is you slowly add acid to the water and you note how much acid can be added before the pH starts to shift. So that's how titration works, and that's how we determine alkalinity. All right, another important constituent that we look at, a water quality parameter we look at, is the Langelier Saturation Index, or LSI. And I did a show on this about a month ago, I think, and we talked about this in great detail, but understand that the LSI is a calculated index which predicts the scaling of water based on calcium carbonate equilibrium values. So once again, the amount of calcium in your groundwater and the pH is going to be important in determining scaling potential in the well. So this is why we look at this stuff, and these kind of things all work together. We have a number of parameters we use in our well health check process where we're monitoring this and really determine what our scaling potential is and corrosion potential, and then, obviously we get into the bacteria as well, but not part of our show today. So components of the LSI calculation, like I say, it's a calculated parameter. This is usually done in the lab, although you can calculate it yourself, but it's just easier to send the sample to the lab and have them calculate for you. The pH is going to be probably the biggest component of the LSI calculation, but temperature, total dissolved solids, calcium hardness, and alkalinity both enter in there, and those are normalized to calcium carbonate. So hardness is calcium carbonate, alkalinity is calcium carbonate. That's generally how you see it reported, but these are the components of the LSI calculation. So this is the actual calculation here. So it's basically the actual pH you measure versus the calculated saturation pH, and that's saturation in calcite or calcium carbonate. So you can see how that's calculated down here below, and basically what that's doing is taking into account the different components there. So total dissolved solids, we're looking at temperature, and we're looking at calcium as calcium carbonate, and alkalinity as calcium carbonate as well. So those all enter in there. We calculate the saturated pH, and then we subtract that from the actual measured pH to come up with our LSI. And so basically interpreting the LSI, now some people will tell you that LSI will tell you the corrosivity of the water, and that's based on the fact that you are stripping out, or because as water becomes more acidic or the LSI decreases, that you are looking at removing a protective coating of calcium carbonate in the well, and that makes it more likely to corrode. That's kind of a little bit of a spurious number, but really, in reality, the LSI is really best at calculating your potential for developing calcium carbonate incrustations or scaling in the well. So if the actual pH of the water exceeds the calculated saturated pH, so you have a positive LSI, that then is going to indicate you have scaling potential in the well. So from that standpoint, this is an important constituent. Its use as a tool to predict corrosiveness in well is a little dubious, but it definitely works well for looking at potential for mineral incrustations to develop. Also, corrosion is another factor that is definitely involved in pH. I talked about that a little bit earlier, but pH is generally going to be the determining factor, especially acidic pH, in determining whether the water in a well is going to be corrosive and it's going to actually attack the metal casing. Now you can uh, defeat that a little bit by using stainless steel. In most municipal wells, use stainless steel. If you're using mild steel in a well, then you really do need to pay attention to the corrosiveness of your well, because some of that corrosion can occur pretty quick. So looking at corrosion indicators in a well, there's a long list here, but pH is definitely right up there at the top of the most important factors. Dissolved oxygen, of course, is a big one, and that certainly helps promote the pH. And then some of these other factors in here as well. Total dissolved solids, obviously, and that's part of your LSI calculation as well. But and also the bacteria components, so we can get microbial induced corrosion. Once again, we're not talking about that today, how that happens, but just know here that as far as corrosion indicators go, pH is generally going to be the most important in your corrosion indicators. And the more acidic your well, the more likely you are to have corrosion going on to your metal. And you can even corrode stainless steel. It takes a lot longer to do, but in conjunction with other things like chlorides, you can actually corrode stainless steel. So it's a myth that it does not corrode. It will corrode, and more acidic solutions can definitely damage stainless steel. So even when we're doing well rehab, using things like hydrochloric acid, we'll tend to use inhibitors to avoid that corrosion from occurring. Even if it's just a brief period during well rehabilitation, it's important to stop that corrosion from occurring. So pH is an important factor there. All right, well disinfection, pH, huge consideration here. We're going to be using chlorine, usually sodium hypochlorite, in the well to disinfect the well. But controlling pH is vitally important to the effective use of chlorine to disinfect the well. And I'll explain here in detail, but it's important to understand that effective use of chlorine is going to be generally best below neutral, generally below a pH of 6. So slightly acidic is where you're going to want to be in order for chlorine to be the most effective. Adding chlorine to water tends to shift the pH to more on the higher end of the scale, becoming more alkaline. So what happens is we have pH shifting out of its optimal range for disinfection. So it is really important to monitor and keep that pH down in the optimal range to have effective disinfection in the well. And this is actually the reason that a lot of disinfection fails, is because they're not monitoring their pH. They're not keeping it in the optimal range. So you shift out of that range, and you might as well just be pouring more water down there for all the effect you're getting. So yeah, you're going to get a little bit of disinfection, but it may not be enough. So you want to keep the pH in that optimal range. Very, very important when you're doing disinfection to monitor the pH, keep it in that optimal range. So the way this works is when you add sodium hypochlorite to the well, or chlorine, you're going to produce hypochlorous acid, which is HOCl, and the hypochlorite ion, which is OCl minus. And then you're going to have spare hydrogen floating around. So now, both hypochlorous acid and hypochlorite ion are disinfection agents, true, but hypochlorous acid is many, many times more effective than hypochlorite. So that's why we want to shift things pH to keep it in, keep our water in the optimal range for producing the hypochlorous acid versus the hypochlorite ion. Their relative concentration is going to depend on the pH. So below 6, you're going to have almost all hypochlorous acid, and that's going to be your optimal range for disinfection. So the pH, of course, is relative. It's important the relative varying proportions of the hypochlorous acid and hypochlorite ions, and so that's why we want to monitor it. In a solution with pH rising over 6, now you start to reduce the proportion of the hypochlorous acid ion and shift it to the hypochlorite ion, and you will virtually lose all your hypochlorous acid at a pH of 9. So it pretty much does not exist, and your effectiveness of your disinfection really tanks. And it's like I say, you might as well be pouring water down there at that point, because you're just not going to get the disinfection effect that you need. And also in free residual chlorination, the higher the pH value, the less active is the residual, because of the lower proportion of hypochlorous acid. So the key to effective disinfection is the proportion of hypochlorous acid you're producing and maintaining in that well during the disinfection period. So this is basically what that looks like in chart form. So you can see on our vertical axis here, we have percent of available chlorine. And then on our horizontal axis, we have pH. So you can see we get below, the crossover point is right about 7.5, where you start to get equal proportions of hypochlorous acid and hypochlorite ion. When you get down to 6, like we mentioned, you are almost 100% hypochlorous acid, and that's going to be your optimal range. You don't really gain too much shifting the pH even lower. I generally like to keep it at least below 7, but if you can get in that pH range of 6 and maintain it there, that's going to be what's going to give you your most effective disinfection, your biggest bang for your buck. So I can't stress it enough. Monitor pH during your disinfection process. Now, what happens if the pH kind of keeps shifting back towards alkaline? Well, that's where we come up with these buffering solutions. Buffering solutions can be really important, and I've actually, back in my early days when I was just learning this stuff, I had some really drastic failed disinfection processes, and we just could not figure why. And I did not really understand the it's like so many people do. You're dumping sodium hypochlorite down the well, and you should kill all the bacteria. Well, none of the bacteria is being killed. The coliform levels pretty much stayed the same. We just couldn't figure this out until we actually talked to a chemical representative. Actually, Cody Chemical helped us out on this one, and they explained what was going on, and it was like a major aha moment for me. And so we took and we actually got some buffering solution. Now, buffering is a chemical process, and we won't go into detail on it, but basically it allows the pH to remain within a narrow range, and that's going to be the optimal range for a disinfection. So keeping it in that 6 or below range. So the use of a buffering solution in conjunction with the chlorine will help maintain that pH in the proper range, and will give you effective disinfection. And in the case of my story, we applied the buffering solution, and the total coliform cleared right up. So it was a pH control issue right then and there. The solution was pretty simple, and I learned an incredible valuable lesson that has stayed with me. So I can't emphasize that enough here. Don't be like me and learn it the hard way. Do it the right way from the start. So now a number of companies out there, I believe Johnson Screens and Cody Chemical, actually offer a buffered chlorine product for disinfection. So it's a all-in-one product that disinfects and buffers the chlorine at the same time. So I see that as a preferred option. If you're just dumping bleach or sodium hypochlorite down the well, it becomes difficult to maintain the pH. If you do it right, spend a little more money, and use a buffered chlorine product for this, you'll get your disinfection done. It'll be much more effective, and you'll be a lot happier off. And this is a case where the money is definitely well spent. All right, so what happens when we get changes in pH in our well? I mean, normally, in most situations, pH is going to stay within a relatively narrow range unless there's some things going on. So we do want to monitor pH, so we understand that. But changes in pH are going to be important because it's going to indicate things going on in our well. So just some things that changes in pH can reflect are, well, under pumping conditions, you're going to aerate the water that's going to come into the well. It's going to mix with the atmosphere, and so you're going to get degassing of carbon dioxide due to that aeration during the pumping process. You quit pumping, and the pH will go back towards neutral or wherever it was. But the degassing of carbon dioxide and the rising of that is going to produce more acidic water in your well. So also the degassing of carbon dioxide, when you send a sample to a lab for pH, it's going to be biased a little bit more acidic because no, it's going to be biased a little more alkaline, I'm sorry, because the carbon dioxide is degassing out of there. So you're removing that acidic component. So it's going to be biased a little high. So you need to really take that into account when you're interpreting pH results from the lab. I generally, sometimes you're required to do that, but I generally prefer using a pH meter in the field to get a more accurate reading. So also, the presence of anaerobic bacteria such as sulfur-reducing bacteria will tend to produce hydrogen sulfide gas as a byproduct of their metabolism. Hydrogen sulfide gas is highly acidic and corrosive to the well. So understanding if you have these types of bacteria in your well and the growth of these bacteria, as they grow and they produce more hydrogen sulfide gas, you'll start to see a shift towards more acidity in your well. So pH, I don't recommend using pH alone as an indicator, but pH is one parameter that we use in conjunction with others that can indicate some potential problems in the well. Because, like I say, pH should be relatively stable, and if you have shifts in pH that are reasonably significant, then you really need to go looking for what the possible cause of that. And another way that changes in pH can manifest themselves in your well is if you have potential contaminants start coming in the well that'll shift the pH one way or another. So relative, significant changes in pH indicate changes in your well, and you probably need to go investigate that and make sure you understand what's going on. I mean, obviously, we can't stop the aeration during the pumping process, so being consistent in your samples when you're looking at pH will help kind of normalize that a little bit, because you'll be sampling under the same conditions and comparing apples to apples. So that's important. All right, so indicators of calcium carbonate scale in the well. This is another way we're using pH. So if the pH is more alkaline, 7.5 and above, if you have hardness above 250 milligrams per liter, of calcium above 180, and an alkalinity above 220 milligrams per liter, these all work together. Like I say, we want to monitor multiple parameters and kind of look at them together. This indicates that you have scaling going on in your well, or you have optimal conditions for scaling going on in your well. The LSI will help tell you that too, but these three parameters together, if you don't have an LSI, you should be monitoring these, and that'll tell you, if you have these conditions here, that'll tell you we have a strong likelihood we have calcium carbonate scaling going on in our well. All right, well rehabilitation considerations. Like I mentioned, well rehabilitation using acid generally is going to require maintaining a pH of 3 or below, during treatment for optimal effect of that acid. So we're going to want to monitor and maintain that pH below 3. So factors affecting the pH in the well, obviously, we talked about alkalinity. We want to understand our alkalinity going into the well rehabilitation process, because that's going to impact the amount of acid we have to use and the concentrations we use. We're generally going to look at the well chemistry. A proper well rehabilitation is going to look at the well chemistry and develop your concentrations of acid and other constituents, solutions you use in your well rehabilitation, and you're going to design that around the existing chemistry of the well to make your well rehabilitation more effective. Alkalinity is going to be a big one, because remember, alkalinity is resistance to the groundwater becoming more acidic. So a higher alkalinity is going to mean it's going to be more difficult to acidify the well to get it in that pH range of 3 or below, and so that's going to mean we're going to use more acid for that. So understanding the alkalinity and some of the other chemistry that's going on, really important. And I will tell you, pro tip, a lot of people do not look at the chemistry of their well before they do well rehabilitation. There's a lot of contractors out there that just go in and do one size fits all. And that's not going to give you your most effective well rehabilitation. You see varying results if you do not understand the existing chemistry of your well before you design up your well rehabilitation program. So there you go. All right. That is our show for today. Thanks for listening. I hope you got a better understanding of pH. There's a lot more to it. You can do a deep dive into the chemistry of pH and all its implications, but we tend to focus on practical solutions here on the Groundwater Guy YouTube channel and at Southeast Hydrogeology, and that's important, because we can spend all day talking about esoteric chemistry, but as a practical matter, it's how does it affect your well, how do we get a well cleaned up, and how do we look for potential problems in that well, and what are some of the indicators. pH is a huge one. Once again, my Lord of the Rings reference, it is the one ring of water quality parameters. It kind of binds them all together. And so it is important to understand pH and its implications. It's not just, looking at the pH on the numbers, seeing how close it is to neutral. It's understanding how we use pH in maintaining and rehabbing our wells for optimal health. All right. Thank you very much. We stream into the Groundwater Guy YouTube channel every Thursday, and also on LinkedIn. We stream live there. This is a live show. And so we do post it up, the recordings up on the Groundwater Guy YouTube channel, so you can find them there. And like I said, liking, sharing, comment really helps us get the word out. And I'm always happy to hear from everybody, pro and con, get the discussion going, and hopefully you found this useful. Lastly, thanks for watching. Don't forget to subscribe to the Groundwater Guy YouTube channel, and I will see you next Thursday.